Now, in this video, I am going to discuss about superposition of n collinear harmonic oscillators with equal frequency difference. That is, superposition of n collinear harmonic oscillation with oscillations, it should be S, with equal frequency difference. Okay, superposition of n collinear harmonic oscillations with equal frequency difference. So here what we assume is we consider n number of harmonic oscillators. Okay, so consider n number of harmonic oscillations. Okay, each oscillation of amplitude is equal to, for example, a naught. Okay, and they have equal phase constant, and the angular frequencies is distributed uniformly. That is, the angular frequency, for example, the lowest angular frequency is omega. Okay, the angular frequency the angular frequencies are in the range omega 1 to omega 2. That means the lowest angular frequency is omega 1 and the lowest angular frequency is omega 1 and the highest angular frequency is omega 2. Okay, and we have got the harmonic oscillations as first harmonic oscillation is, let it is represented by x1 is equal to a naught cos omega 1 t. Second harmonic oscillator is x2 is equal to, it will be a naught cos omega 1 plus del omega times of t. Third harmonic oscillation is x3 is equal to a naught cos omega 1 plus 2 del omega times of t, like this. Okay, and the nth harmonic oscillation is, for example, xn is equal to a naught cos omega 2t. So here you can see the lowest angular frequency is omega 1 and the highest angular frequency is omega 2, as I have stated here. Okay, and the difference between any two consecutive the difference in frequency between two consecutive harmonic oscillator is del omega. So here this thing you keep in mind. From this equation you can see del omega, the frequency difference between two consecutive oscillators is del omega, which is equal to omega 2 minus omega 1 divided by n minus 1. It can be written like this, which is equal to del omega divided by n minus 1. Okay, so we have got this. Now what will happen upon superimposition? After superposition, what you will get? X will be equal to x1 plus x2 plus like this plus xn. What is x1, what is x2? So x1 we have already written. X1 is equal to a naught cos omega 1t. X2 is a naught cos omega 1 plus del omega times of t, like this, a naught cos omega 1 plus 2 del omega times of t. Okay, like this, plus at the end I have a naught cos omega 2 times of t. Okay, so now we know that this x is the real part of complex function z. Okay, so x is the real part of complex function z. Okay, so this gives, that is, z is equal to a naught, we can write like this, a naught e to the power I omega 1t plus e to the power I omega 1 plus del omega times of t plus e to the power I omega 1 plus twice of del omega times of t. Okay, like this, plus e to the power I, here you can write omega 1 plus n minus 1 del omega times of t. Okay, like this. So for example, this equation number we have for example, this equation number 1. Okay, and this equation number 2. Now you can see that in equation 2 the term inside the bracket are in GP series. Okay, inside this bracket it is in GP series, isn't it? It is in GP series. Okay, and what is the common ratio? We can find the common ratio. So this z can be written like this. Z we can write here a naught times of Okay, sorry. We can write here, if we write like, if we take e to the power I omega 1 t as common, then we can write here, for example, 1 plus b square, okay, plus like this, plus b to the power n minus 1. Okay, so here what I'm taking here, b I'm taking as e to the power I del omega times of t. Okay, so this term is in GP series. It is clear, it is very clear that this is in GP series. Okay, so the term in the bracket, okay, the term or the expression, you can say the series, you can say the series inside the bracket, is in GP series, geometric progression series, with what is the common ratio? Common ratio b, isn't it? The common ratio is b. So what you can write, therefore what you can write using GP series formula, e to the power I omega 1 t b to the power n minus 1 divided by b minus 1. Okay, as per formula. So now we know that b is equal to e to the power I omega t, I del omega t. So it can be written as a naught e to the power I omega 1 t in bracket e to the power I n del omega t minus 1 divided by e to the power I del omega t minus 1. Okay, I'm just substituting the value of b, okay, from here. So next we can do some mathematical tricks here. So z, from here z can be written as a naught e to the power I omega 1 t. So if you take e to the power I n del omega t by 2 as common, and in the denominator e to the power I del omega t by 2, so here I am getting as e to the power I n del omega t by 2 minus e to the power minus I n del omega t by 2 divided by e to the power I del omega t by 2 minus e to the power minus I del omega t by 2. Okay, so what we are doing here is, from this expression we are taking e to the power I n del omega t by 2 common from the numerator, and from the denominator we are taking this term as common. Okay, so why you are taking? For our convenience, we'll get to know why. Now what you can write here, we can write here is a naught e to the power I omega 1 t, writing the exponential term as exponential I. Okay, half n minus 1 del omega t by 2 del omega t. Okay, so what I'm doing here is, you can understand why I'm writing from this expression to this expression. And here we have got sine half n del omega t sine half del omega t. Okay, why I'm writing here? Because this comes under the formula like sine theta. We know that sine theta can be expressed as e to the power I theta minus e to the power minus I theta divided by twice of I. Okay, so on that basis we can write here. So next, for example, this is equation number till now we have given equation 2. So this is equation number 3. Now we have got one equation. From equation number 1 we can see that omega 2 minus omega 1 divided by n minus 1 is equal to del omega. So putting the value of equation 1 here. Okay, from equation 1 what you can write, omega 1 plus half of n minus 1 del omega is equal to omega 1 plus half of omega 2 minus omega 1, that is equal to half of omega 1 plus omega 2, which you can write as average of omega 1 and omega 2, which you can write as omega average, AB average. Okay, for example, this is equation number 4. Okay, now so what is omega AB? Is the average angular frequency of omega 1 and omega 2. So what does equation 3 become now? This equation 3, what you can write? So from equation 3, what you get? Z is equal to a naught e to the power I omega average t. Okay, why? Because you can see why I've written like this. Next, sine half n del omega t sine half del omega t. Okay, from equation 3. This is equation number 5. Now if x is the real part of z, okay, we know that we have already said the real part, since z is a complex function, the real part of complex function z is x. So this gives x is equal to a naught e to the power I omega average. Okay, sorry, it will be a naught times of sine half n del omega t divided by sine half del omega times of t, and here cos omega average of t. Why cos term? Because we are considering the real part of z. Okay, because z is equal to, z is the complex function, cos theta plus iota sin theta, like that, we know that. Okay, so this is equation number 6. We are only considering the real part of z, which is x. Okay, so now at the end what you can write, x is equal to am cos omega m t, where here what you can write here, am is how much, am is equal to a naught times of sine half n del omega t divided by sine half del omega t. Okay, so this is the modulation amplitude. Okay, modulation amplitude. So this is the entire expression for the superposition of n collinear harmonic oscillators having equal frequency difference. I hope you have understood. Thank you very much.